Today we will be talking about retrieval-based language models. Okay, so let's get started. So, so let me take a poll here first, right? I'm sure that all of you are using ChatGPT, right? So, what are the tasks you typically use it for? Coding. Okay, cool. Writing emails. Good. Retrieving some factual information. Correct grammatical errors. Cool. Summarization. Good. Okay. So in all of these tasks, I think you are actually acting as a gatekeeper and a verifier, right? I mean, if you're using it to generate code, you are the one who is actually verifying the code, right? You're not using it blindly. Similarly, to compose an email, I mean, you have to verify, otherwise, you send that mail to your prof and anything can happen after that, right? So I'll tell you where do I use it for, right? So one thing that I use it for is creative writing. If I have to create a notice, I don't want to go and write, all that flashy stuff. I just give it facts and it creates a flashy notice for me. Here, the example that I'm showing, it's, writing a story in some specific style. Good. If it makes a mistake, I don't mind. It's okay. Repercussions are not much, right? And these models, have performed really well even in exams, right? In exams, if you make a mistake, it's okay. It's just 1.1% down score, right? It's not, a matter of life and death. It's not that you're giving medicine to someone. Even if you score low in USMLE exam, it's fine. It's just a score, right? And one thing that I have noticed, the biggest issue that I have noticed with these models is something called hallucination. So this is a real world example. My last submission was about point-wise mutual information and using it to quantify hallucination. So I thought, let me do some related work using find some related work using ChatGPT. So I typed the query, what is the use of PMI in NLP? It gave me something. And I was shocked because it looked like my work has already been scooped. People already know. I mean, it's already there, out there, right? Okay, then I said, okay, can you give me some citations for the above examples, right? And that's where the fun begins. The first citation is point-wise mutual information for language modeling. I went to Google Scholar. There's no paper with this name. It cooked it up. Right? And this is true for all the papers that are there in the citation. None of the paper exists. So this is a classical case of hallucination. If I were not the verifier, if I had copy pasted this related work in the paper, then definitely my paper would have been scooped. Right? Yeah. And that is what happens when you do that in real world situation. There have been cases where there were repercussions. For example, there was a US lawyer, poor guy, he did not verify whatever ChatGPT returned, and he presented some cases which were fake, which were hallucinated by the language model as a precedent in the court, and boom. Similarly, Air Canada had a chatbot and there was a legal case against them as well because, some user forced the language model to say something that he wanted, and then it became a binding contract on the company to, respect that, whatever that chatbot said. So this is a big problem, and that this is one of the major reasons what stops these language models from being deployed in critical scenarios, right? And in places where a company can be held liable for its responses, right? Another issue is again verification. It itself claims that it can make mistakes. This is the disclaimer that it gives. Right? And even if you prompt it for some verification, right? This is the link, hyperlink that it is providing. This link is working, but notice the titles. It doesn't correspond to what it generated earlier. So even if you use it to verify its own output, there are issues, right? And definitely there is knowledge cutoff, right? When you're pre-training the language model, you take all the information, all the documents up to a certain date, right? For example, this is a query about a person who is a professor now in some university, and ChatGPT doesn't know about him, of course, right? Okay, and then definitely there are learning failures, right? These models do not attain zero perplexity. They don't know that they have not memorized everything. They can still make mistakes, right? So with all of these in mind, how should we go about using it in a real world scenario? Let's motivate it by taking an example, right? So these language models, I'm calling them parametric language models because they store all the information in the parameters, right? At the time of training, you show it all the information. For example, the capital city of Ontario is Toronto. This is the information with which you train the model. It will put that information in its weights, and at the time of testing, when I am giving a query, let's say the capital city of Ontario is, I expect it to generate Toronto, right, from its own memory. It has not provided anything extra, right? So this is, I like to think of it as, closed book exam, where when you're preparing for the exam, you read the entire book, you have to mug it up. But when you are in the exam, you have to answer only using the memory that is there in your parametric space, right, in your brain. Now, is it mandatory? Right? There are certain exams which are open book, and in the real world, why not? Right? Contrast it with an open book exam where model is allowed to use external knowledge even at the time of testing. And this is, I mean, in the real world, this is what happens, right? It's okay if a doctor goes and opens his book and finds, checks the facts, right? So this is what retrieval-based language models is, essentially. Right? In addition to its own parameters, it is relying on access to the information at the time of testing as well. It is answering not just from its own parameters, but also from the information which it can access at the time of testing. Right? And when you're using the book in an exam, there are three ways in which you kind of use a book in an exam, right? If it's an open book exam, one is that you solve the problem on your own, and then you use it to verify, right? You use, with your own mind, whatever answer you can come up with, you come up with that answer, and then you go back to the book, search for the query, right, and check if your answer is correct or not, right? So I like to call it as output interpolation, where you use the external knowledge after you have solved the question yourself, right? So KNN language models is one work which falls under this category. We will look into it. The other is intermediate fusion. That is, you start solving it and you are stuck. Then you go back, search in the book, retrieve some information, access it, and then continue. And then again, maybe you need to stop and go back and search in the book and then get more information and then continue, right? So I like to call it as intermediate fusion, and we will discuss a work retro here. And notice that here we may have to even change the architecture of the language model, right? Because when you have external information coming in between while you are processing the input yourself, then you may have to somehow change the architecture as well, right? And the most common and non-intrusive way of using external information is called RAG, or retrieval augmented generation. And this is essentially input augmentation. What you're doing is that, okay, you're given a query, you go and search for that in the book, right? You retrieve the relevant documents, right? And now once you have retrieved the relevant documents, you give it to the language model, which will attend on that information as well while answering the question, right? So this is essentially input augmentation, right? And this is the technique which is most popular. We will look at two works in this category. They're RAG and REL. They're contemporary work. They came almost simultaneously, right? But before we use the information, right, we need to search in the book, right? I mean, if you are given a book, if you don't know how to search in it, then that book is useless, right? So this process of searching in the book is called retrieval, and this is the first thing that we will cover today. We'll discuss various retrieval techniques and see how it works, right? Okay, so how would you search in a book? Let's say I give you a physical book and you have a question. How would you go about searching in that book? Let's say you do not know about that book either, right? You're looking at it for the first time, so you don't have that information in your memory. So how will you go about searching in the book? Index. Okay, where do you find it? At the end of the book. Okay, anything else? In the index, right? Cool. So that's right, and that is what will motivate our first approach. That's essentially an inverted index, but not the index, right? It's mapping keywords to the pages. These pages are, let's say, individual documents in the corpus. The entire book is a corpus. Each page is a document in the corpus, right? The index is an inverted index, which is mapping, the page, the documents which contain specific words. You have a specific word, you go and search for a specific word in the index, and then it maps you to the pages which contains. That's an inverted index, right? So good. And this is what motivates the first retrieval method, which is sparse retrieval, right? So in sparse retrieval, what we do is that we represent any document or a query as a bag of words, right? So essentially, let's say the query is what is NLP, and here each dimension corresponds to a word in the vocabulary, right? The length of this vector, the dimension of this vector is going to be size of the vocabulary, right? Whatever is the vocabulary size, and you will have non-zero entries here for the tokens which are present in the input, whatever you are trying to index, right? Whatever you are trying to find a representation for. In this case, we are representing the query using a sparse vector, right? The query has 3 tokens. What is an NLP? And correspondingly, only these 3 are the non-zero terms here. Everything else is 0, right? So this is a representation of a query, and this is sparse representation because only a document will contain only few words, right? So most of the entries are gonna be 0, corresponding to the words which are not there in the document or the query, right? And similarly, we will represent, let's say, for the sake of argument, we have 3 documents in the corpus, right? Using a similar representation, we will represent each document. So here, the document contains what is life, candy is life, and the non-zero entries are for what, candy is, and life later on, right? So at somewhere for life, we will have a non-zero entry here, right? Whatever, some x, which is non-zero, right? And these are normalized so that they sum up to 1. Right? Similarly, you will have a representation for each of the documents, right? And now if you have to find the document which contains the query, what will you do? How do you figure out which document contains the query? Right, yeah, so dot product or cosine similarity, right? Because when you take a dot product, only those entries will remain where both are non-zero. If a particular dimension, if a particular word what is there in both the query and the document, only then the corresponding entries are going to be non-zero, right? So you will have non-zero entries for only those words which occur in both the query and the document. That's what you want to search for, right? So here, this is going to be non-zero and this is going to be non-zero, right? Only what and is. Everything else, you will have 0 here, you will have 0 here, and everywhere else, right? This is what you get when you take a dot product of Q and D1, right? Similarly, you can compute the dot product of the query with the other documents, right? And you pick the one which has the highest similarity or the highest score, right? Now, in this example, what do we get? the first document happens to have the highest similarity score. But is this the relevant document? Right? So what is happening here? Which document is relevant for this query? Right, D2. We want D2 to have the highest similarity, right? So what is happening here? Why is it that this question has the highest similarity with document 1? Correct. All the words in the query are assigned an equal weight, and in a sentence you will always have many stop words, right? These are the common words which you will have in every document and in every query, mostly, right? I mean, people don't ask keyword queries where they will ask NLP, right? So people are gonna ask, form a sentence, what is NLP? And what and is, in this case, what is happening is that what and is are overpowering NLP, right? So we have to discount the frequent words. And how do you do that? So, okay, I hear multiple things. One is stop word removal could, yeah, that is obvious strategy, that we should remove the stop words, find all the stop words and remove them. Good. The other thing that I'm hearing is TF-IDF. So it looks like people already know, a lot of people already know about this thing, right? So yes, TF-IDF is what we do. Essentially what we do is that for each token, we figure out whether it is a rare word or a very frequent word, right? We figure out in how many documents this token appears. Let's say if I see a word the, right, it will appear in all the documents, almost all the documents. So this is not an important word. If I have a word the in the query, this will not give me any information about the query as such, right? So the information will be contained in rare words. For example, what is NLP? In the query, word NLP is what contains the information mostly, right? So what we do is that we so this is what we had earlier, term frequency, where we had number of times a particular token appeared in the document divided by total number of tokens in the document, the fraction that we had earlier. This was the term frequency that we see that we had earlier. We multiply it with inverse document frequency, and inverse document frequency is simply saying this is the total size of the corpus, right? And in the denominator we have the number of documents containing the word T, the token T, right? Right. So if this is low, if the denominator is low, numerator is constant, right? If the denominator is low, then IDF is going to be high. We are going to give more weightage to those terms, and vice versa. If for example, if a particular token appears in every document, right, then it's going to be right. Okay, good. So yeah, this IDF takes care of the rare words or the stop words, and then BM25 is a sparse vector representation which further modifies the term frequency term. And the intuition here is that if let's say there is a very big document in the corpus which contains almost every word, right, we would like to penalize that, because it will come up in every search query, right? In every search result you will have the document because it contains almost all the tokens in the vocabulary, right? So we normalize that with this term here, which essentially D is the length of that document and this is the average length of the document in the corpus, right? So that is one thing that it takes care of. And the other thing that it takes care of is that if in a particular document a particular rare word occurs multiple times, let's say a particular word NLP is coming 20-30 times, do we really want to give that much importance to that word, or do we want to saturate its importance at some point, right? So the other term K1 essentially takes care of that saturation effect, where if a particular rare word is appearing multiple times in the same document, then we don't want to go beyond, let's say, 5 or 10 occurrences of that. We want to count all of that as equal beyond a certain point, right? Okay, so this BM25 is one of the most popular technique for sparse retrieval, right? So to find the top documents, it's not feasible to go iterate over all the documents and compute the dot product and find the one which contains which has the highest score, right? to speed up this computation, what we do is, what you were suggesting earlier, inverted index. It's essentially, for each word, we know the document IDs which contain that word, right? So whenever we are given a query, we can search for those tokens, query tokens in this index, then we will know the documents which contains that, and then we can restrict our search, right? So this essentially helps in speeding up the entire process. And Lucene is one of the software which builds that, which provides, an example is a software which implements this. Okay, so what is the issue with this? What issue do you see with this token based matching? Right, it's a classical NLP problem, right? If you have a word bank, it can mean
The sense is not.
right, the sense, the context is not captured, the sense is not conveyed, and another issue is that out of vocabulary is another thing, and then synonyms is another problem, right? You are searching for a particular word, but then the document or the corpus contains synonyms of those words, then you will not find a match. Yeah, right. So you're saying that there might be a document which contains actually information about that topic, but it uses some synonyms of the words of the tokens in the query, right? And so it will not even appear in the search. On the other hand, if there is a document which is just mentioning those things in the passing, will appear in the search results. Right? These are some obvious examples, some obvious drawbacks of having a sparse lexical overlap, right? Lexical search. Right. So, and obviously, the solution is essentially dense representation, moving from sparse representation to dense representation. Right. So, what we do is in dense representation that we would encode all the documents in the corpus. So, these are all the documents that we have in the corpus. These are their corresponding embeddings. These are dense embeddings. Right. Now, at the time of testing, when you get a query, you can find its dense representation, right? This is the dense representation of the query, and then you can go and search in the entire corpus, right? And return the top documents that have the highest score, right? So there are two questions here. One is, how do you create these embeddings, right? Can you use out of the box BERT model, let's say, to document to create these embeddings? Can we use that? What are the pros and cons? Sorry, and that's fine. We'll use Ankh for that, and I think dense representation will take some care of it, right? Document size. Okay, so we'll ensure that each document is 512 tokens, not more than that, right? So at an intuitive level, the issue with using any out of the box embedding model here is that the queries and the documents are in different space, right? One is asking a question and the other is answering the question, right? Who told the model to align those two embeddings? Why do we believe that the embedding of a query will be same as the embedding of a document by using any out of the box language model, right? I mean, for example, BERT is a masked language model. It is trained to fill the masks in between. It is not trained to, Roberta, for example, is trained for next sentence prediction task, right? So it is not trained to map a query to a document. And that is why we need to create special models, right? We can create, I mean, it's okay, we can create single model for this, for both query and document encoder, but we definitely need some special model. We can't use out of the box model as it is. I mean, we can use it, but it may not give us good performance, right? So when we are training these models to create the embeddings for query and the document, what do we want, right? We want that if a particular particular query can be answered using a particular text chunk, right, then the query embedding that I get for that particular query should be close to the document embedding in the low dimensional space, right? So that is the idea. To begin with, it will not be the case, right? So what do we need to train this, right? How would the training data look like? Question answer pairs or query and document pairs, right? So I need a query and I need a document which contains the answer. So why do we need negative samples? Right. So if we naively say that, just maximize the dot product of query and document, it will what is the fallback weights that it can learn, which are kind of redundant. It can maximize the score to 1 for any query and any document. You're just maximizing it. You're not contrasting it. You're not saying that this document contains the answer, but there are another document, D1, D2 negative, D3 negative, and the other documents that are there. Let's say there are n documents in the corpus that we have, right? We want to say that bring its embedding close to D positive, right? But take it far from D negative, right? Now, okay. Now, can I compute the similarity with respect to all the documents in the corpus at the time of training? Right? If let's say there are millions of documents, then I cannot compute the similarity with respect to all the documents. So what we need essentially is some sort of negative sampling, right? How do we sample the negatives? So this is the positive passage, and we want the query and this P plus to be close to each other, right? And we want this query to be far away from all the other passages, and it is too expensive to consider all the negatives. So we resort to contrastive learning, or we sample the negatives randomly, right? So this is the idea that's what we want. We want to begin with the query positive document and the negative document will be kind of equidistant, and after the training we want these to be close to each other, query and positive and query and negative, we want them to be further away from each other, right? Okay, now there are different works and they differ in the way they create the negatives, right? So how would you go about creating the negatives? Two solutions. First is that you statically fix negatives. That will not work because it will only learn to distinguish one positive with respect to fixed number of negatives. Those only whatever negatives that you have chosen for a particular query, right? The other alternative that you suggested is good, and that is called in batch negatives. The advantage there is that the batch is gonna be formed randomly, and therefore we hope that it will see every other document during the training, right? So that is called in batch negatives. And then DPR, what it does is that it does something more interesting. What it does is that we essentially want to distinguish it from the hard negatives, right? We essentially want hard negatives. I mean, if let's say there is a query is about what is NLP, right? Now there is a document which talks about feelings. Obviously, these two are going to be in separate spaces, even if you're using a out of the box language model, right? It will have difficulty in distinguishing between documents which are close to each other. Let's say a document which talks about specifically NLP, and then there is a document D2 which is mainly about machine learning and mentions NLP in the passing. And then there is a document 3, which is broader document and talks about AI and then ML and then NLP, right? This is the most relevant one for us. And these are kind of the documents where the model will struggle, right? These are called hard negatives. And one way of creating this is, fall back on the sparse retrieval. Do sparse retrieval, right? and the documents that are in the top, those are the ones which are difficult, and use that as negative, right? So that is what DPR does. And contriver is another work. What they do is that, for this is an unsupervised dense retrieval model, where let's say you do not have a query and document pairs, right? So what they do is that they, from the same passage, they will take two chunks, right, and then they will treat them as positives for each other, right? So this is one way of creating, basically this is unsupervised way. Okay, so we covered how to train the embedding models for creating the embeddings. For you may now you may have two different embedding models for document and query. So you may have a query embedding model, and you give query to it, and it will give you the query embeddings. And you can have a separate document embedding model, right? And you give document to it, and you get document embeddings. Alternatively, you can have a common model as well, right, where you prefix this query with some special tokens, an identifier that tells you that this is, I want query embedding, this is query embedding. And when through the same model, when you're embedding a document, you can prefix it with a special token which tells you that I need a document embedding, right? So both the options are there. Right? Okay, now once we have created once we have learned these embedding models for embedding the query and the document, right, at the time of testing, you will get the query, you will find its embedding. Now you have to search in this big corpus of all the embeddings, right? In the case of sparse embedding, we used inverted index, right? Now how would you go about searching in this case? How do you find the k nearest neighbor of this vector in the entire space? So let's say this is the 2D representation, this is where your query lies, and you want to search in its neighborhood and find the k documents d1, d2, d3, dk which are closest to it. So what you are suggesting is essentially some sort of clustering, right? What you are saying is that whatever documents that you have in the space, you kind of cluster them. Let's say these are the 3 clusters that I create, right? And then I can have a representation of the cluster, of each cluster. This is also an embedding, right? Now I have, once an embedding comes, a query embedding comes, I have to search, first figure out in which cluster it lies. Right. So for example, if I create 3 clusters only, right, and I have 3 million total documents, right? In the first search, I am finding similarity with respect to only these 3 cluster centers, center 1, center 2, and center 3, right? And I restrict my search space to 1 million. I can go on doing this recursively, right? So essentially, I have reduced the search from order n to, what are we doing here? Order log. Good, right? Good. So that is what you were suggesting. Let me try to phrase your query. I think your doubt emerges from the way we are selecting our negatives. You are saying that because we considered hard negatives as well, and those hard negatives might create problems, right? I mean, for the example that we took, that there's a document that mentions NLP, and then there's a document which mentions ML and NLP. We have pushed apart ML and NLP, right? And but if we have pushed it apart, they will be further apart from each other, right? So relatively, yes, they will be, if a query is about NLP, it will, okay. So if a query is, let's say there is a query about NLP, right? It will lie somewhere here. This is let's say it is query about NLP, right? And let's say this is the cluster in which it lands in the first case. For sure, if it will be far away from the documents which are talking about astronomy, right? Because we have ensured that, and it is easy for it to learn that as well. It will definitely push those away, right? However, what you are saying is that because the query is about NLP, within this higher cluster, there will be a space about NLP. There could be a space about some other computer vision. I mean, definitely this query will be closer to computer vision than astronomy, and we want that as well. So this cluster, with the help of that contrastive loss, where we took hard negatives, what we ensured was that a query about NLP should be closer to these are the NLP documents and slightly further away from the computer vision document. And if we get a computer vision query, it should be closer to the documents which are about computer vision. All of them at the top level, maybe at the first level, both of them are gonna be in the same cluster. So both the query about NLP and query about CV, will land in the same higher level cluster, right? But when we go one level deep, when we further classify that, maybe we will have different breakings. There will be a cluster about NLP, there will be a cluster about CV, then there will be a cluster about, let's say, time series model, right? And if there is a multimodal thing, it will be somewhere in the middle, right? Somewhere which will match with everything, right? So that bifurcation between NLP and CV will come maybe in the next iteration. Does that make sense? Right? So each cluster itself is very big. You are right that when we are first creating clusters at the top level, computer vision and NLP will be in the same cluster. But when we go deeper at the second level or third level or fourth level, they will get bifurcated. And multimodal models are going to be somewhere in between both, right? It's somewhere equidistant from both the queries, both the topics, right? Okay, so good. We covered one way of creating this index hierarchical tree structure. The other interesting way is locality sensitive hashing, right? So what it does is that it randomly starts with a classifier. Let's say this is a random classifier that it has, right? Randomly initialized weights. So what this classifier is doing is that it is partitioning the entire space into two parts, right? This is, let's say, this is the positive part of it and this is the negative part of it. So this is 1, this is 0 with respect to the first. I can further initiate another random classifier. This is also partitioning the space. This is 1 side of it and this is the 0 side of it. And I can go on and on, right? Now look at what it has done. It has also given us some sort of partitioning of the space. The core idea remains same. We have to create partitioning of the space, right? And for each partition, we also get a kind of a hash map or a sparse representation, right? So this dimension is the 3 is the number of classifiers that we have here. We can take multiple classifiers, hundreds and thousands of classifiers, let's say. I will have a sparse representation now for each cluster, right? So this is essentially a hash map, right? That is why it is called hashing. This is a hash map for this part of the space, right? Now when a query comes, right, I can hash it and figure out where it lies. I can pass the query through all of these classifiers that will give me the corresponding hash and I can map it. Or alternatively, these are now sparse embeddings. I can create an inverted index as well, right? So these are the two popular techniques for approximate nearest search, and these are approximate, right? These are not exact nearest search. One of the reasons is what you mentioned earlier, right? That it may happen that a document which is relevant, we might have pushed it further apart, right? A document, let's say, which mentions both computer CV and NLP, it's a chance that we might have pushed it outside the boundary, right? So therefore it is approximate nearest neighbor search. Okay, so graph-based search, we already discussed this earlier, right? This is the cluster-based mapping, and Annoy and Fias are the softwares which implement these two, and these are quite popular, very easily available. Okay, so till now what we have discussed is essentially a by encoder scoring, right? What we did was that we took the query, embedded it, we took the document independently, embedded it, and then scored them later on, late interaction, right? And the advantage of this was that we could embed all the documents offline and save it in the index, right? And then search. Do you see any potential negatives of this, of doing it this way? Right, but we have learned the model, right? That the whole idea of learning the retrieval embedders was to ensure that query and documents come in the same space, right? So we have taken care of that to a certain extent by training these embedding models specifically, right? So in terms of contrast it with sparse embeddings. Can you think of anything wrong here or anything which is lacking? Okay, so what is the difference between dense embedding and sparse embeddings? Let's focus on the word dense and sparse. Sorry, sparse? Okay, yeah, that is the definition of sparsity. A lot of elements are going to be zero, but focus on the the embedding vector, right? Each word in the vocabulary had a representation, separate representation in that embedding vector, right? In contrast, here we have, let's say, 1024 dimensional embeddings only, right? In the dense representation, we are forcing the entire information in the document, which could be much longer than 1024, to be represented by a dense embedding. Essentially, we are losing information at the granular token level, right? Right. So there is some loss of there are issues with the representation power of the specific model, right? So how can we go about improving it? Is there a way of improving this? What would be the best way of finding the similarity between two documents or a query and a document? How would you go about it if you have to preserve the token level information as well? Fine, multiple dense embeddings, you can cover the space, but you will never be able to go till V, right? You will never be able to go to, you will not be able to account for all the tokens in the document, let's say, and because still those are going to be less than the number of tokens, whatever it is that you're taking. Okay, so the solution here is simple but very expensive. The idea is that you embed the query and the document together. Let's say in the BERT model, you concatenate the query and the document, and then pass it through the model, right? And then take the embedding. So this embedding has taken into account all the tokens, right? Now, what is the issue with this? The documents, but they were earlier as well. Earlier also we were passing the document through the embedding model, right? Good. So that is the major drawback, that in this case, how will you go about searching for the document, right? You have to take all the documents. Their embeddings cannot be pre-computed because now these are contextual embeddings. Now the documents are contextualized on the query and vice versa. Earlier, the document embeddings were independent of the query. They were not contextualized on a given test query, right? Here you have contextualized them, right? So there are no embeddings that you can compute a priori and store them, right? You can't do that. So this is very expensive, and therefore it is not possible. Best what you can do is that you can re-rank using this model. That is, use this dual encoders, by encoders, fetch 100 top 100 documents. Now amongst those hundreds, you can re-rank them using this cross-encoder, right? And but then still, if you want to, I mean, still this is expensive, right? You will have to call the model 100 times at least, right? Is there anything else that you can do? I mean, can you have best of both the worlds in some sense? Have the document embedding stored, and then still, while computing the score, have the query attend to each token in the document instead of just one embedding. And then you okay. So what you are saying is that you first train this model, right? You have already trained these models, right? You have a query embedding model, and then you have a document embedding model. Now you are saying that if you are training this for re-ranking, let's say, right? When you are training this, once you have this model, now you are relying only on the re-ranker to create the embeddings. Notice the difference between the two, right? Re-ranker is only re-ranking, right? It is only kind of looking at hard negatives, right? So I'm not sure whether the embeddings that you get after that will those be able to distinguish between, let's say, astronomy and NLP. I don't know about that. I mean, I'll have to think about it, but upfront, I don't think whether that is going to work or not. Okay, so let's quickly discuss a popular approach for re-ranking. This is called Colbert. So what they do, so this is kind of a hybrid thing. It's a mix of both the worlds, right? What they are doing is that offline they compute the document embeddings, right? This is offline. At the time of storing, they are storing all the token embeddings. So storage cost increases because you are now storing every token in the document, embedding for every token in the document, right? Now, once you have fetched the top 100 documents and now you want to re-rank them, in order to re-rank, what you do is that you now you compute the query embedding, right? So this is token 1 of the query, token 2 of the query, and token 3 of the query, and this is token 1 of the document, token 2 of the document, token 3 of the document, and token n of the document, let's say, right? Now what you do essentially is that for this token, let's say, right, you want to search whether this token lies in the document or not. That's what that is what sparse embedding was doing. It was kind of searching that token in the document, right? Here we want to search for the embedding of this token, right, amongst these embeddings in some sense, these token embeddings. I have to search for this token in these, right? So what I can do is that I can compute its similarity with all of this. So T1 dot D1 is the similarity of token 1 of the query and token 1 of the document, and this T1 D2 is the similarity of token 1 the document with token 2 of the document, right? And I take the maximum similarity one, right? So that will give me the token which is closest to that, and if there is no token which is closest to that, this max will also be very low, right? So for each token I get the max score for the first token. Similarly, I get similarity score for the second token and max score for the third token, right? And I add them to give me the similarity score, right? So this is essentially taking care. I mean, it is essentially instead of using just one embedding for the entire document, it stores the embedding of each token in the document, right? And then compute the similarity at the granular level. It's some sort of compromise between the two, cross-encoder and bi-encoder, and it is very efficient and most popular technique that is used for re-ranking. Okay, so another way of retrieval, this is another popular technique, hypothetical document embeddings. So the idea here is that we motivated learning a new model by saying that query and the documents lie in separate spaces, right? So what they do here is that they pass the query through a language model like GPT-3, right, and prompt it to generate a document which may potentially contain the answer, right? So they map the query to a potential document which may contain the answer. Now you can use any out of the box embedder because right for embedding this document, because now it is in the same similarity space as the other right, as the documents that you have indexed, right? And notice that this can also be used for used with sparse encoder, right? So this can also be thought of as query expansion. You are given a query, you are essentially expanding the query to include more words which are related to that, maybe some synonyms and all of that. And now once you have included the synonyms, you can go back and search using BM25 or a sparse. Because the major issue was with BM25, one of the issues was synonyms. Synonyms will not get matched. So this is called a hybrid approach as well, where you use a dense or language model to expand your query, and then you search using BM25 using the expanded query. So we cover cross-encoder re-ranking, and we also looked at hide as one of the ways, right, where you can use kind of a hybrid approach, or where you use a language model to modify the input query. Okay, so till now, what we have done is that we have created the retriever using an index. We created and we learned an embedding model to embed the query, right, and the retriever, the query and the passages, and search using an index. Can I somehow use a language model itself to tell me the document, to give me the document given the query? I mean, these language models are powerful enough to memorize the entire corpus, right? We know that. I mean, they have so many parameters. You can train them to just train them over the corpus and memorize everything, right? So taking this particular paper, differentiable search index, takes a completely different view of the retriever, right? It says that how about training a language model which takes a query as input and just spits out the document ID. Just assign a document ID to every document, and the language model that you have, it will take the query. Let's say this is a sequence to sequence, so it will have an encoder and then a decoder. So the encoder will give me some representation of the query, and the decoder will attend on this representation and just spit out the document ID, right? I mean, this is completely different from whatever we have seen till now. And as a proof of concept, they actually do that, right? So the idea here is that we learn to encode and retrieve using the same language model. So this is the query. It goes to the encoder, right? And it gives me the representation. V123 is the vector representation of the query. This is the document, goes to the encoder. V456 is the document representation, is the representation of the document. And when this goes to the decoder, it simply spits out the document ID, document 456. Right, this is the document which can answer this query. When I say this V456, this embedding, this also spits out doc 456. It maps, essentially, it says that this content is mapped to this document ID. Right, so it is mapping this content to this document ID, right? And they call this as indexing. This is what they call as indexing, right? Right, and search is nothing but mapping this. Retrieving is nothing but mapping this to the corresponding document ID, which will contain the answer, right? It's a very simple approach, and there are two tasks for which you are training the model. One is indexing task and the other is retrieval task. So similarly, you will have some identifier here, right? So this is with indexing, and you will say document, and then the model will spit out the document ID, and you will say retrieve, and you will say the query, and the document will retrieve the document ID, right? And two important question is, how do you represent the document when you are training this language model, and how do you represent the doc ID, right? So they essentially work with three different ways of document representation. Direct indexing, essentially whatever the document is, you take the first L tokens of it. Set indexing, you convert that document into a set, remove stop words, and use that as the document while embedding that, right? And inverted index essentially means that you just take any random contiguous chunk of the document and map it to the corresponding document ID, right? And and direct indexing is what they find to be the most useful in their experiments. Okay, now to represent the doc IDs, the most common thing that one can do is that have a token for each document ID. Right now, your vocabulary will increase from whatever tokens that you had earlier plus size of the corpus, total number of documents in the corpus. Right, this will be your total vocabulary, and you will have to do a softmax over this dimension in the output layer. Right. So this is basically unstructured atomic identifiers. The other is that you treat the document ID as a string. So you have DOCID5. This is a string. You just decode it one token at a time. Right. So this is again the string representation of the document ID, and it's a naive structured string identifier. And the other, they also create semantically structured identifiers. The idea about the semantically structured identifier is that let's say the entire document is divided into chapters and sections and subsections, and let's say each subsection is a particular passage that is the smallest chunk that you want to index, right? So the document ID may contain some structure in the output. It may have chapter number first, the chapter 7, section 5, subsection 5.2. Right, this is kind of a structure that we are inducing using the known structure of the document. But what they try is essentially they don't assume any structure which is given to them. They create the structure by looking at the embeddings of all the documents using, let's say, some out of the box language model, and then clustering them the way we created it earlier. Right, so you at the first level, let's say you create 3 clusters, right, and then further each cluster is subdivided. Right, and let's say this is the leaf node. Each passage that you are indexing, it will be represented as 2 and 3, and then 3. What is this 3? This is the 1, 2, and 3. The third document in this cluster. Right. So at the leaf cluster, you will have some documents. Let's say right. So this last 2, 3. This is at the first level. 2. This is at the second level. You're going to the third cluster, and then this is the number within that cluster. You sequentially number each document, right? Okay. So these are the results that they have. Again, this idea is very preliminary in its preliminary stages in some sense. It's kind of a proof of concept, right? So they're not dealing with very big index, right? They're going up to maybe 250 or up to 300k documents that they are indexing. Right, and if you look at this, these are the different ways of so this is the dual encoder, which is the baseline that we have. Right, these are the baseline numbers. These are the different ways of encoding the document ID. This is the atomic document ID where they're taking a softmax over the number of document space. This is the naive string that you have, doc ID 5, and semantic string doc ID could be chapter, comma, subsection, comma, section, right? Or alternatively, you can create the cluster that they created. And if look at the jump that they get, it's kind of on a subset of the data, NK 10K. Their hit at 1 is 48.5, and the maximum that they get here is 22.1, almost the double. Right, so I mean, this has opened a new direction in some sense in the entire retriever space. And finally, this is the last bit that I want to cover. Recall that when we started talking about retrieval, we said that we can use the index to search, right? Is there any other way that you can search? Index is one way, and when I give you a physical book and you have to search for something, where all places do you search for it? You don't open. Exactly, right? So index, what we saw earlier, and table of contents is another place where you can actually search, right? So now how about providing the entire table of context in the prompt, table of content is not going to be huge, right? These days language models can process 32K context, right? And I prompt the model to, you know, give me the subsection number which can potentially answer the question, right? Because there is going to be text heading of each subsection, and query can potentially be mapped to that, right? So this is another approach, table of content search. We prompt a language model with TOC and a question and ask it to generate the chapter title subsection which contains the answer, right? And we can also explore an LLM, you know, answering it in a zero-shot fashion without training it. And alternatively, we can train a language model as well with certain books and certain table of contents, and then at the time of testing, we can give some other table of contents and ask it to search, right? So this is what this approach proposes. This work is still under submission, right? And the idea here is that the language model will get table of content and the query, right? And the output should be the leaf node of the table of content, right? Leaf node is, let's say, subsection level is a leaf node that we want, right? And because these language models are powerful enough, I can prompt them for, you know, I can prompt them to restrict their output, you know, to a specific format, right? So these are some preliminary results, and these are the different, in each row we have a different book that we are indexing. We compare with DSI and BM25 search, and we show that, you know, in some cases, for example, in social science, the gain over DSI is 19.2 points and gain over BM25 is 17.5 points, right? So this is a promising approach. This work is still under submission, and these are the preliminary results that you're seeing, right? So yeah, so what we have covered till now is the retrieval methods, right? Tomorrow, what we will do is that we will go back to our analogy of how to use the book. Remember, we looked at 3 methods of using the book. One is, you know, once you have solved the question and then you go and find something, verify in the book. The other is while solving, you go back, find something, come back, solve, then solve for some time, go back, come back and solve, intermediate way, right? The other is where you read the question, go and search in the book, find the relevant passage, read it, read the question, and then solve the query, right? That is RAG. So we will go over each of these 3 models, these 3 approaches and architectures for them, and how to train those models. Thank you.